Good afternoon, everybody. Welcome to I²CNER seminar. My name is Takata from Thermal Physical Properties Division of I²CNER. So today, we have a very famous professor from Saga University, Professor Masanori MONDE. So first, I would like to introduce him. Professor Masanori MONDE is graduated from the University of Tokyo and got a PhD in 1976. Then he joined the Saga University as an assistant professor. Then 1978, he was promoted to associate professor. Then 1989, he became a full professor at the Department of Mechanical Engineering, Saga University. Since 2002, so he has been serving as a director of the Institute of Ocean Energy in Saga University. It's a very famous institute, research institute. So his main research topic consists of two areas. The one is the boiling heat transfer, and the other one is the hydrogen energy systems. And there are lots of researchers that are doing the research on the boiling heat transfer in Japan, so including myself. And so from the foreign researchers, so we are called Japanese boiling mafia. And he is the boss of the Japanese boiling mafia. Today, he will talk about the hydrogen systems, especially he's studying the thermal analysis of hydrogen storage systems. So we'd like to invite Professor MONDE. So please.
Good afternoon. Thank you, Professor Takada, for good introduction to me. So I am great honor to be here and to present my recent research on hydrogen. So hydrogen studies, and I have started the research related to the hydrogens about 15 years ago, and as Professor Takada introduced me, my main research field is boiling heat transfers. This is a side work, but recently this topics becomes a main field of my research. Anyway, so I am great honor to introduce my recent research. And shall we start my presentation? Why energy storage system is needed using the hydrogen in the futures. As you know, how energy do we have on the Earth? As you know, energy on the Earth from the solar, but solar energy has been produced from fusion energies, as you know. And we have huge energy from solar. And some amount of solar energy are storage for a long year as fossil fuel, as you know, oil, coal, and natural gases. And recently, much focus on natural energy as renewable energy, which are not stored. Maybe energy come on the Earth, but most of energy is reflected into the atmosphere and also the cosmos. How do we storage these energy and how to use these energies? And medium terms that we call the biomass fuels. Biomass fuel is stored in the plant for some years. For example, the plant, every about 40 years, so tree died, and so some energy is stored in the soils like this. Anyway, we have 3 different kinds of energy on the Earth. One is fossil fuels, which has been stored for long, long years. And second one is stored energy for medium term, not long. And this is third one is renewable energies, like this. So renewable energy is energies are classified into solar heat, ocean energy. Tidal power is a little different from the come from solar, but energy tidal power is called a kind of renewable energies. And wind power, solar array, geothermal. Anyway, those energies are called the renewable energies. And next step is the, as you know, the fossil energy is stored on the Earth for long times. But those energy has been exhausted within the, for example, the oil within 42 years. And for the natural gas is would be exhausted within 60 years, and coal within 122 years. And uranium, a little different kind of energy, but also the uranium exhausted within 100 years. But the renewable energy can be used forever. But as you know, the sun activity does not work forever. But maybe it is impossible for us to, the sun will die. Maybe no one believes sun will die in future. Anyway, so we have the much energy from fossils, but fossil energy is gradually decreased, and finally fossil energy has gone. But this energy can be forever. So how do we use these renewable energies? So we account how amount of renewable energy do we use. Okay. Now, data is a little old, about 21 years ago. But Japanese economical activity has been not changed after this year. Maybe energy consumption in Japanese economical activities not so changed. Anyway, a huge amount of energy is supplied to Japan. Like this number is too much. So we use another unit. This energy is one Japanese energy. So very easy, one Japanese energy. And we use much amount of electricity consumption in Japan, huge amount energies. But we cannot remember this large number of power. So we call simply one Japanese power. This is a new scale. We use how amount of energy is stored on the earth or some amount of energy from the solar energy. We measure these scales. Very simple. Okay? So the total primary energy supply to the world is about 16 Japanese energy. But the population, Japanese population is 60s. So Japan use a lot of energy compared with other countries. Okay, maybe about 4 times larger than average energy consumption. And so the solar energy from on the spheres, so 70,000 Japanese energy, huge energy, come from solar on exospheres. But solar energy really reaches on the land is almost 120,000 Japanese energy. Compare with this amount. So 2/3 of the solar energy reach to on the earth. 1/3 energy is reflected on the atmosphere. Anyway, solar energy pass through the atmosphere to the earth is around 2/3, like this. And available energy of the solar energy is around 1/10, like this. And rainwater, much energy we have. But potential of the hydropower is very small amount, like this. And this is, we account solar energy into Japan is about 82 times larger than 82 times of Japanese energy. Maybe the solar energy reach to the Japan, the economical, sorry, I cannot remember, exclusive economic zone, okay, 82 times of the Japanese energies. And exhausted heat in Japan is 0.66 Japanese energy. Anyway, we account the how amount of renewable energy can be available as energy. So now much interest on the solar power. Okay, so solar panel on the roof can make electricity. If the according to these estimations, about a quarter of Japanese power can be obtained from solar power. This is the maximum one. And estimated wind power is around 3.1% Japanese power. But recently, the wind power can be installed on the sea area. So European country, for example, Denmark, the many wind power are on the sea. Maybe this estimation is little smaller at the present. But according to this tables, Japanese needed power is short from renewable energies. But I think the renewable energy should be introduced to cover the Japanese required energy. So to use this renewable energy, so we have developed new technologies. Okay. So this is a simple why hydrogen is attractive now. Okay. Hydrogen can be converted and produced from various primary energy resources, especially from renewable energies. Okay. And hydrogen makes recycling of renewable energy like this. And so we have electricity from the renewable energy, so like this. So best way is to use the electricity directly. But this is a dream. So the electricity from the renewable energy does not meet needed power. So we need the storage systems. One way is hydrogen, the other way is batteries. And we stored energy as hydrogen or batteries at a short time to meet the needed energies. So we developed the fuel cells which makes the electricity from hydrogen, and exhausted one is water only. And water is used to produce the electricity through the renewable energy. And we have these cyclings of the energy networks. And if we use these networks, so we move towards low carbon society through the hydrogen. Maybe this is the reason why the hydrogen is very attractive now, I think. So, and this is a primary energy. So for example, fossil fuel and bypass those are renewable energies. So those primary energy stored as a hydrogen, which is a secondary energy. And so hydrogen has many different kind of passes like this. And hydrogen energy can be used, for example, the fuel cell, which makes heat and electricity. So the path is very important. Why the hydrogen is attractive like this. And this is examples why the hydrogen is useful like this. This is a path from primary energy to the hydrogen, and hydrogen is used in the stationary fuel cell systems. For example, the electricity is supplied to the housings. During the supplying, the housing need the electricity and the heat. Both are efficiently used, so and high efficiencies like this. But another way is fuel cell vehicles. So now the vehicles is driven by the fossil oil and natural gases. But if we can produce hydrogen and fuel cell works high free efficiency, so we use the to the fuel cell vehicles like this. So this is another ways like this. And now we discussed on the why fuel cell vehicle is important like this. So fuel cell, FCV is a kind of electric vehicles. Then the electricity is produced by the chemical reaction between hydrogen and oxygen. And FCV has advantage in long driving range and diversity of fuels. And the FCV is a clean power generation and being friendly with environment and new technology expected to create a low carbon society. Anyway, the hydrogen society using the fuel cell contribute to reduce the carbon dioxide. So now, recently, the two vehicles are proposed. One is battery electric vehicles. The other one is fuel cell vehicles. We compare both vehicles. So, for example, total efficiencies. This is a well to wheel, which means that we consider digit out the energies and final usage conditions. This is a wheel. Well means digit out oil. Anyway, we take account into the origin to the end of the energies. So the electricity is 0.94 megajoule per kilometer, but hydrogen is also a little larger, but nearly equal the total efficient. And COT exhaust, slightly larger fuel cell vehicle is slightly larger than electricity, but much different characteristics are driving range and fueling times. EV need much longer times to charge the electricity, and EV drives around 100 to 200 kilometers, not so long ways driving. But for fuel cell vehicles can run 2 or 3 times longer than EV. And the fueling time is much shorter than electricity charging times. But disadvantage is network for charging the energies. So electricity is network is existing, but the hydrogen network does not exist. So we need to construct networks for hydrogens. And this is a budget, so small investment for electricity vehicles, and large investment is needed for hydrogen. And this is the systems of electric vehicles and fuel cell vehicles. So we compared systems for 2 different vehicles. So EV battery electric vehicle is much simpler than fuel cell vehicles. But the consensus is car is driven by electricity. This is a dynamo. This is a dynamo. So anyway, so last year we visited the European countries, so EU and Germany. So they said cars are driven by electricity. So this is the electricity, and also this is the electricity. But how can we get electricity? So this internal combustion energy. This is the simple ways. So hybrid car, and this is a battery, and this is the other one is a fuel cell. Anyway, car moves to the electricity cars. And according to the comparison between batteries, car, and fuel cell vehicles, so maybe the battery cars are operated in this region. So size is small, and driving range is shorter than 400 to 4 or 300, something like. Anyway, battery car covered in these areas. But the fuel cell vehicles can drive longer and larger. For example, bus is operated by the fuel cell vehicles like this. So we developed the fuel cell vehicle societies. We need the infrastructure to fuel the hydrogen into the fuel cell cars. So recently, last year, car company announced from 2015, fuel cell car actually will be sales, and the price of the fuel cell car is announced. So at that time, the infrastructure should be needed. Like, and so now 100 stations will be established until 2015. Okay, and Kyushu area maybe 10 stations will be built, and Tokyo area is maybe 40 stations will be built. Anyway, so we need the fuel cell hydrogen stations. This is the overview of the hydrogen stations. So quickly explains the hydrogen is deformed from natural gas, and hydrogen is compressed, and compressed hydrogen is supplied at 35 megapascal to fuel cell cars, and the other path is more high pressure hydrogen up to 87.5 megapascals. And why such high pressure hydrogen is needed? So to keep longer distance drivings. Anyway, so car company requested fuel station up to 70 megapascal, otherwise, if possible, 87.5 megapascals. In order to get such high pressure hydrogens, so the hydrogen temperature is increased during the filling the hydrogens. This is the issues from thermal point of view. We face some troubles for hydrogen fillings. This is a hydrogen tanks. So from the point of strength of materials, so the lightweight and high strength tanks, and so this is the customer required rapid filling and safe filling. But the rapid fillings, during the rapid filling, the hydrogen temperature quickly increase, sometimes higher than 85 Celsius. But under the regulations, hydrogen temperature in the tank should be lower than 85 Celsius. This is big problems to construct the hydrogen station from thermal point of views. So how to reduce temperature rise is another discussing point. And this is like this. Hydrogen is quickly filling into the tank. Temperature goes up. How to reduce hydrogen temperature lower than 85 Celsius. So simple way is we supply much cooled hydrogen. Okay, cooled hydrogen. So now the car company requests us to keep supply hydrogen gas at around -40. -40 is a little high hurdles. Anyway, this is a discussing point. We studies how to we analyzed how to say the temperature rise during the fillings. Okay. So this is our models to estimate the hydrogen temperature during the fillings. This is a simple energy equation. Maybe textbook tell us. So this is a energy equation for this hydrogen tanks. This equation can be available for any cases. Okay, not hydrogen. So we use thermodynamics textbooks give us this equation. But before us, most of research ignore this term. This term is the heat transfer term. Heat transfer term is very complicated. And first analysis might be done by I and Dr. Peter, who worked in the Kyushu University, these teams. But he moved to Kyushu University. So before he moved to Kyushu University, Dr. Peter had worked 4 years with my lab. And there, at that time, so we analyzed this heat transfer like this. Anyway, this equation is given any textbook, thermodynamics textbook, okay, and like this. So, and this is a governing equation and initial temperature and mass balance and this also mass and state equation, equilibrium state equation like this. And the problem is like this. This is a heat transfer terms. So, and connecting condition is like this, okay? So we need the heat transfer coefficient between gas and walls. And we need that's all. This is connecting between the gas and walls. And we solved those equations simultaneously, but very complicated. And this data was obtained by us at Power Tech in the Canada, and we got these temperature rise during the filling hydrogen, and the measuring point is here. This TATB, TETD are temperature sensors, and sensors stored here, mounted here, and like this. And this solid line was obtained by our softwares. Maybe acceptable result might be obtained. This is the first verifications our software is going well. And the next step, this is a recent result from NEDO project. And this is a hydrogen supply conditions. Hydrogen supply with change with times, like this. And this hydrogen supplies from 3 tanks. Okay, 1 tank supplies the hydrogen, but the pressure at the supply tank becomes lower. So next high pressure tanks switched on to supply here, and 3 banks are used to supply the hydrogen to these tanks. And the temperature of the hydrogen like this. Okay, we used those data to estimate the temperature in the hydrogen temperature in the tank, and measured data is black dot point is measured temperature, and the red line is estimated from the software, our analytical result. Maybe very good agreement we have, but after 100, so a little different between the measured and the estimated result are different. We understand why this different occurs, but today skipped it, the reason why this different occurs. And the analysis tells us temperature distribution in the world. So within 180 seconds, within 3 minutes, so heat does not penetrate deeply into the walls. Maybe temperature change occurs only near the surface area, like this. So maybe the heat transfer coefficient of outside. So we ignore outside condition. Just we focus on the heat transfer coefficient on the inside world, like this. And so we recording the governing equation and boundary conditions. So this is a governing equation and boundary conditions are non-dimensionalized. So finally, we got this a little complicated equation. But we check the structure of this equation So those 9 parameters are 9 parameters determine the characteristic of hydrogen temperatures in the tank during the filling tank. Okay, and we check the 6 non-dimensional parameters. So we put here. So this is estimated. This is temperatures in the tank is a function of. This is the filling time and non-dimensional parameters, which are given like this. If we specify tank characteristic, for example, the tank volume is 160 and inner area is something like this. So anyway, we specify tank. We have the thermal property of the tank and the thickness, something like this. And anyway, BI, we said BO number 1, BO number 2, and this non-dimensional 4 parameters are determined by tank characteristics. Okay? And other parameter is T. This is the filling time, and this is a filling enthalpy, and this is a initial temperature and initial enthalpy. Initial enthalpy cross given by the initial temperature and initial pressure, like this. Anyway, finally, the filling process can be determined 6 parameters: initial pressure, initial temperature, final pressure, final temperature, final filling time, and temperature, feeding hydrogen temperature. Anyway, 6 parameters are enough to determine the hydrogen characteristics. So, like this. For example, under regulations, upper temperature should be equal to 85 Celsius. So we put 85. So we have 5 independent parameters. Anyway, the filling process can be determined 5 parameters only, okay? Like this. For example, the filling hydrogen temperature is a function of initial condition and final pressure and filling times. If we have want to take filling times, which is given also P0, T0, PF like this. If we have this equation, and this equation is installed into the hydrogen stations, so hydrogen station can supply hydrogen to the fuel cell tank quickly. And we check based on our softwares, and we consider actual operating conditions. So we choose the 300 point within actual operating conditions, and we set the data combination P0, T0, anyway, 5 parameters. And by applying least mean square method for 5 parameters, independent parameters. So we finally this equation, okay? But many coefficients we have, but this parameter is automatically determined for specified the tank, okay, specified tank. Also, filling time has 48 coefficient because the filling time curve a little complicated. Okay. Anyway, we look into the, for example, how initial temperature influence the pre-cooled hydrogen gas. So 2 parameters, 3 parameters. 3 parameter means quadratic curves, not straight. And this is for the filling times. This is the J0, J1, J0, J1. Pressure, okay. Effect of pressure is almost linear. Okay. Anyway, we have many coefficients for unspecified tanks. And if we have a specified, I skipped here, so we quickly calculate the effect of the supply hydrogen temperature against the initial pressure, initial temperature. If the initial temperature becomes higher, so supplied hydrogen should be cooled until around 40, like this. So I skipped. Anyway, these graphs are quickly obtained from the equations. And I now serve as a member of international filling, how to say, the code. Anyway, if those equations will be used to determine the condition for filling. So now the conservative filling case, no communication. No communication means no data. So, but if the communication is applied between station and fuel cell vehicles, we have initial temperature, initial pressure, and coded tanks characteristic. So we have automatically this equation can be available. Okay? So I insist on this internationalized standard communities strongly. This equation can tell us how to fill the hydrogen like this. So now the community tell us to use lookup table. But if this equation can be available, so lookup table is not necessary. Lookup table can be replaced by this equation. And this equation is installed into the stations. So automatical filling can be done for any fuel cell tanks with communications. And this is a standard deviations of the equations. Maybe most of case can be predicted within a few percent. Maybe this is enough accuracies, I think. And next storage method is metal hydride or organic material for hydrogen storage. This is Professor Akiba's main fields. I don't know the details of the metal hydride and metal organic materials for hydrogen storage. But we studied the heat treatment of metal hydride. So starting of hydrogen fuel tank is metal hydride. But the metal hydride tank is too heavy. Most of automotive company refused to use metal hydride now. So the Professor Akiba look for lighter hydride, organic hydride, which has been studied now in Kyushu University. Anyway, to store hydrogen into the metal hydride. So this is a chemical reaction, metal hydride and hydrogen. This is a after chemical reaction. This is heat. It should be removed during the absorption. Anyway, speed of chemical reaction depends on how to transfer the heat quickly. This is my field, okay? And the skipped expected characteristic for the MH is high thermal conductivity. This is my field. The other one is another field. Anyway, how to manage thermal conductivity, thermal treatment for hydrogen metal hydride. This is the equation, and we solved this equation, and shortly show you. This is a metal hydride tanks, and how do we manage heat transfer in the metal hydride in these tanks? This is a fin, and we designed finned metal hydride tank, which are enough requirement from the NEDO. And we calculate how temperature change during the absorption of in the metal hydride. We calculate how temperature change and how concentrate change like this. Sorry, this is the temperature. And this is the concentration of hydrogen. So at 120 seconds, so hydrogen absorbed like this. And this is the full. Red means full of the hydrogen absorption. And the chemical reaction almost finished about 840 seconds. And this is another technique to heat transfer enhanced. And this is a finned designed by us. And this is a circular fin, and this is the radial fin. By using this these fins, we enhance heat transfer, by which the absorption process is quickly done. And this is the numerical calculations. And this is the time. And this is the finish of the chemical reaction conditions. And this is the absorption process going into the center, and also like this. Those calculations also developed by our lab. And so, finally, hydrogen as a secondary energy can be produced from diverse energy resources such as renewable energies and fossil energy. Now we have big problems, as you know, the Fukushima nuclear power plant damaged by the tsunami, and we face the crisis, nuclear crisis like this. Anyway, fossil energy is fission energy from the nuclear reaction. Fossil is oil or coal, like something like that. Sorry. And hydrogen can be converted in electricity and heat at high efficiency via fuel cells. And in addition, hydrogen contributes to carbon dioxide reduction and makes creation of new energy society possible towards the future. So I quickly explained why hydrogen is focused now at the present. Thank you for your attention.